In section 9.3, we're going to learn 2 more tests, so a couple more tools to put in our toolbox in terms of determining when a series will converge and when it might diverge. So the first is the integral test. All right, and the integral test looks like this. This is the integral test itself. So if I have, if I can write a function for the last term in that series, and that function is positive, continuous, and decreasing, then I can use the improper integral and find out whether that converges or diverges. And the series itself will converge and diverge just as the improper integral does. Right? So if the improper integral diverges, then this sum will diverge. If this improper integral converges, then the sum will converge. All right? F has to be positive, continuous, and decreasing for x values that are greater than or equal to whatever we start with here for our series. All right, so in this case it's n equals 1, so the lower limit of my improper integral has to match up with that 1, and then the values of x over which f has to be continuous, positive, and decreasing also match up with that initial value of n. Okay, when we find this improper integral, if it converges, then it will converge to a specific value. That does not tell us the value that this series converges to. Right? It just tells us that the series does converge. The values that they converge to will, in general, be different. So for that function, we have to show that it's positive and continuous, and that it's decreasing for those x values. And in order to show that it's decreasing, we have to show the derivative and show that the derivative is always negative for any x values that are greater than 1. All right. Once you've established that the function meets these conditions, use the improper integral and see if it converges or diverges. And we've talked about how the value that the improper integral converges to is not necessarily the same value as the series. All right. So when we look at an example like this, we want to determine whether it converges or diverges. The series, we have n over n squared plus 1. For us to decide if we can use the integral test, we need to first show that this function is continuous, positive, and decreasing. Because this starts with n equals 1, we're going to use the x values greater than or equal to 1. All right, so at least for this first example, I want to find f prime. I want to show you the process of working through f prime. So we have x squared plus 1 squared as our denominator. When I take the derivative of this, I have to use the quotient rule. So the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator. And I get x squared plus 1 minus 2x squared over x squared plus 1 squared, which gives me negative x squared plus 1 squared. So notice that this denominator is always positive. All right, and this numerator will be negative for any x values greater than 1. So that is how I justify the fact that f is decreasing for x values greater than or equal to 1. So once I go through that, I can move on and find the improper integral. So if I think about doing the integral of this function, I could use u substitution, and I would get 1/2 ln of u plus c. And so the improper integral of this function from 1 to c, as c approaches infinity, I do the integration. I have this as my result, and then I do ln of, I substitute c and 1 in as I subtract, and then look at the limit as c approaches infinity, and I get infinity for that improper integral. So this improper integral diverges, which also means that the original series diverges. All right, let's look at another example. Here we have 1 over n squared plus 1. Notice here we had n over n squared plus 1. So in the same way, I create a function that represents the nth term of this series. In the same way, I would have to show that the derivative of this function is negative for x greater than 1 to prove that it's decreasing. And then I do the integral there. This is an arctangent, the 1 over x squared plus 1. So I make that substitution. The limit of arctangent as the argument approaches infinity is pi over 2. Remember that arctan of infinity means the angle whose tangent is equal to infinity, and that is pi over 2. And arctan 1 is the angle whose tangent is equal to 1. That's pi over 4. So this this improper integral converges to this pi over 2 minus pi over 4, so we get pi over 4. All right. That means that this series converges, but again, don't make the mistake of thinking that the series will necessarily converge to pi over 4, because it won't. We just know that they either both converge or both diverge. The values are not necessarily the same.